Hello, and thank you for joining us. Today's webinar is Use of Hydride Generation, Cold Vapor, and Solid Phase Chelation for Signal Enhancement and Interference Reduction in ICP-OES and ICP-MS. Our presenter today is Fred Smith, Technical Product Manager for Teledyne CETAC. Please feel free to submit questions throughout the presentation, and Fred will respond via email after the webinar has concluded. As always, this webinar is being recorded and will be available within a few days. Okay, now I'm going to go ahead and turn it over to our presenter, Fred Smith.
Thank you, Shelley, and thank you everyone for attending today's webinar. This is the last webinar in our series this year in 2021, and we're going to be talking about two separate techniques for sample preparation and sample introduction in atomic spectroscopy. One will be hydride generation or cold vapor, used in either ICP-OES and MS, and an offline sample preparation technique using solid phase chelation. So in the first part of the presentation, we'll look at offline and the online sample preparation, which is done when sample introduction is done using hydride generation or cold vapor generation. Either one can be then connected to ICP-OES or ICP-MS for trace element detection. And then in the last part of the presentation, we'll look at an offline only sample preparation technique, followed by sample introduction with a traditional ICP-MS nebulizer like a cross-flow nebulizer. And that we're going to term a batch mode solid phase chelation technique. So first, we'll describe the hydride generation cold vapor technique. In this, we'll mix a liquid sample with an appropriate reducing agent chemical to convert certain analytes to a volatile hydride or to an elemental form that's volatile. That hydride or that form is then swept by an argon carrier gas flow into the host ICP-OES or ICP-MS for detection. Again, in this case, the argon nebulizer gas will be acting as a true carrier gas because it's not being used to generate any type of a sample aerosol. Instead, certain analytes are going to be converted to a volatile form, in this case, a hydride. So this slide shows the general series of reactions that are used for this type of reaction, meaning hydride generation. And at the bottom, you see the metal hydride is released as a gas along with a byproduct of hydrogen gas. And that's an important note in the general design of the hydride generator. We want to minimize any turbulence from the generation of that hydrogen gas byproduct. At the very bottom of the slide, you see a list of elements that can form a volatile hydride. Now, these will not all form under the general same conditions. However, we are going to focus on some of the more common ones, namely arsenic, antimony, and selenium for the hydride reaction. Mercury can also form a volatile hydride, but in this instance, we are going to then generate it into a volatile form by a different reaction, and that reaction is cold vapor. I will point out, again, up at the top of the slide, the reagent that is generally used to do the reduction, and that is sodium borohydride. So the hydride generation reaction can be nearly 100% efficient, and that enables greatly enhanced detection of more difficult to detect elements such as arsenic, antimony, and selenium. In addition, the hydride-forming analytes are separated from any non-hydride-forming matrix components. So those will simply be pumped out to waste and do not get to the ICP or ICP-MS plasma. So that can greatly simplify method development when you don't have to worry about interferences from common matrix components such as sodium and calcium. So we'll first start with a schematic, and one thing that I'll point out, which is probably the most important part of the design, is the split gas flow. So on the right side in the middle, you see a port where it says carrier gas. That typically will be the nebulizer gas flow routed from the host ICP or ICP-MS. Then on the left side, above a fluoropolymer filter or membrane, is a additional or makeup gas flow. Okay? So the carrier gas will be used to move the generated hydrides through the system. They will then permeate through, since they're a gas, through the filter. And then that additional gas, which comes in above the filter, then helps to transport the volatile hydrides to the host ICP-MS. That split flow is very important for getting the best signal-to-noise ratio. The other part in the middle, specifically where it says frosted post, which is a glass component that has a very high surface area, we're going to then send the sample solution with the analyte, with the reagents, flowing over that higher surface area, and that's to help get the best efficiency for release of the volatile hydride. There's a droplet separator to prevent any droplets from coming up and striking the filter. And this overall then is what is described as the gas-liquid separator. But again, I want to point out the important part of this are the two separate gas flows to help balance out the reaction, specifically the generation of the hydrogen gas, and again, to get the best signal-to-noise ratio. So here is a front-on picture of the hydride generation system we're going to use, and that's called the HGX200, and it's offered by Teledyne CETAC. So some of the things that I've pointed out here, we'll start on the left side. You see the inert membrane. We'll take another close-up view of that so you can actually see the disk. There is a manual gas flow meter if you require it. That's mounted on the front of the unit. And then on the right side, I've pointed out the gas-liquid separator area, and specifically that one red arrow is pointed towards that glass post, which you see has been frosted to give a very high surface area as the solutions flow across to release the volatile hydride. At the bottom of the piece of glass, of course, is a drain, and that's to remove out any of the excess waste liquid. And again, what we're going to be sending to the ICP plasma is a volatile hydride, a gas. So we're not sending any liquid aerosol toward it. So in the general hydride generation setup, and this is a more expanded schematic, on the left-hand side, again, you see the gas-liquid separator. But on the right-hand side, the HGX200 will have a series of mixing blocks, which can be used to then mix in the sample with the appropriate reducing agent, in this case, sodium borohydride. The mixing block just below that says acid, you can use if you need to further acidify a sample. That's because the sodium borohydride solution is actually kept at a basic pH so it stays stable. So in some cases, additional acid may have to be added. Also note here the two pumps. And this depends upon the type of peristaltic pump you may have on your host ICP. On the analytical pump, you may have to use 2, maybe 3 channels to move the sample solution and reagents in. In some cases, you can dedicate another peristaltic pump if you need the extra channel to pump out the drain. And it's very important that you have to have the speed of the pump on the drain moving faster than the influx of the sample solution and the reagents, because you do not want liquid building up inside the gas-liquid separator. That would, of course, cause instability. So these are some nicer close-up pictures. You can see then again on the left-hand side the frosted glass post. I've also pointed out the 2 mixing tees or mixing blocks. The one on the bottom is for additional acid in case you need it. The one just above is used for the sodium borohydride solution, so of course you're going to use that. And then above there is a mixing coil, and that is to get good mixing of your your sample solution with the sodium borohydride reagent. Once that's done, that mixture then will flow across that frosted glass post with a high surface area, and then the volatile hydride will be released. Another close-up picture. Here you can see a little bit more detail of the flat disc shape of the inert membrane. Okay? That's giving us a little bit of a buffer then between the ICP or ICP-MS torch and the reaction and the gaseous byproducts that are going on inside the gas liquid separator. But then importantly, you see the input of the two gas flows into the HGX-200. The carrier or nebulizer gas flow on the right, and the additional or makeup gas flow, which comes in just above the inert membrane. So you will then adjust these two gas flows to get the best signal-to-noise ratio during the analysis. And of course, you would do that first with a tuning solution, adjust those gas flows, and then start to put through your sample solutions. So for applications, we're going to use this hydride generation device, the HGX-200, first to show some improved ICP-OES detection of arsenic, antimony, and selenium, and we'll look at this in a variety of biological, food, and water sample types. So first, before we approach the analysis, pre-reduction steps are necessary to ensure the intended analytes are in the correct oxidation state before the hydride reaction. And this is very important. And we're going to focus on the main three that we mentioned earlier. We have to convert arsenic 5 to arsenic 3, antimony 5 to antimony 3, and selenium 6 to selenium 4. So these reactions are all pre-reduction steps before we would react the sample with the sodium borohydride reagent and generate the volatile hydride. This slide in this table shows the detail of the pre-reduction procedures that are used. This is for arsenic, antimony, and selenium. We use the same procedure for arsenic and antimony, and that's preparing the standard with potassium iodide and ascorbic acid in 10% HCl. Potassium iodide acting as the reducing agent. For selenium, it is different. The selenium is boiled in a relatively concentrated 6 molar solution of high purity HCl. The arsenic and antimony reactions are allowed to run for up to 5 hours. The selenium is simply a boiling reaction for 15 minutes. So operating parameters with the host ICP-OES. So for the most part, the conditions are similar between the use of the standard nebulizer and that of the hydride generator. However, of course, as we saw in the earlier pictures, the hydride generator has this additional argon gas flow. The nebulizer gas flow is a little bit less. We'll set it at 0.5. That goes through the gas liquid separator, and then we add the additional gas above the membrane in that additional side port. And in this case, it's only 0.2 liter per minute. And then you adjust those two flows to get the best signal-to-noise ratio. If you do not have a makeup gas flow on your host ICP-OES or ICP-MS, although most ICP-MSs have that now, you can use the little manual flow meter on the front of the HGX-200 to do that additional gas flow if needed. So one point, I'll point at the bottom of the slide, the ICP-OES model that we used for these sample measurements is a PerkinElmer Avio 500. The comparative standard nebulizer is a glass concentric type with a cyclonic spray chamber. So, hydride reactions and standards. Standards and samples are mixed online with a hydride generator using a 1% sodium borohydride solution in 0.1 molar sodium hydroxide. So it's a basic solution in order to keep the reagent stable. This, in some instances, you may need to add that additional acid through the mixing block. If samples are sufficiently acidic, you may not have to do that. But just so you keep in mind that that solution is kept in a basic form so it stays stable during the course of the day. Calibration standards were then prepared from pre-reduction stock solutions at 1, 2, 5, and 10 ppb. The diluent for the arsenic selenium was 10% nitric acid, similar to the sample digest we're going to look at. The diluent for the selenium standards was 10% HCl. So first, I'll give you one example of a calibration curve, and this is for arsenic at the 189 nanometer line, 1, 2, 5, and 10 ppb, and a very good correlation coefficient, 0.496. So that performed very well. And then here is a summary of the correlation coefficients. They need to be at least 995 to be useful for analytical work. The system certainly met that, and the recovery of a 1 ppb standard, reading that back against the curve again, was excellent, all right around within 5-6% of 1 ppb for arsenic, antimony, and selenium. So first, before we looked at the samples, we wanted to get an idea of the detection limits. 10 blanks were measured using the standard glass concentric nebulizer, cyclonic spray chamber setup, and the HGX-200. For the standard nebulizer, 2% nitric acid was used as the blank. The blanks for the HGX-200, of course, were reagent blanks. And for the arsenic and the antimony, it's the potassium iodide, ascorbic acid in 10% HCl. And for the selenium, it was 10% HCl. So here you can see the detection limit comparison. The hydride generation reaction, because it is so efficient, nearly 100%, can really push detection limits down considerably below a part per billion with the hydride generation technique, far below the standard nebulizer. So we're actually getting down towards 1/10 of a part per billion with the hydride generation technique. So some of the samples we're going to look at then. So first, we'll look at arsenic and antimony. And one is a biological standard. This is NIST 1947 Lake Michigan fish tissue. The second is an estuarine water from the National Research Council in Canada, SLU-2 from the St. Lawrence Seaway. This will have total dissolved solids content of about 1%. So that's putting it at about 1/3 of the salinity of open ocean seawater, to give you an idea of how that compares. So the digestion methods, we won't go into all of the details, but here is where the methods were referred from. The Lake Michigan fish tissue, the FDA analysis manual EAM 4.4. And for the NRC SLU-2 estuarine water, EPA test method 3010A, those were then used to digest those two sample types. The microwave digestion system that we did use was the CEM Mars 6. So again, we have to do first the digestion of the two samples, and then we have to do the sample pre-reduction steps. So then the digest of both the fish tissue and the estuarine water are reacted with the appropriate pre-reduction reagents. In this case, the potassium iodide, ascorbic acid in HCl, and the samples are allowed to stabilize for 5 hours before analysis. In addition, a laboratory control standard, or LCS, at 2 part per billion of arsenic selenium was also run. That was, of course, digested as previous per the US EPA method, and then the pre-reduction reagents were added, and the resulting solution allowed to stabilize for 5 hours before analysis. So for the laboratory control standard, reading against the calibration curve, again, we got excellent recoveries of the 2 part per billion for arsenic, antimony, 94 and 98% respectively. And excellent agreement for the arsenic that was certified in the Lake Michigan fish tissue. Fortunately, there wasn't an antimony value, but we have excellent agreement for the arsenic. Then the estuarine water, where we could get some idea of the antimony recovery. Again, the arsenic recovery was quite good, a little bit higher at 117%, but still quite good. The antimony measured at about 0.55 versus a reference value. This was a data from a literature compilation for antimony. Recovery a little bit low at 82%, but again, the value is not certified. So then next, since we have different pre-reduction techniques, we wanted to look specifically at selenium. In this case, we looked at it in 2 different reference materials. We looked at it in NIST 1643F, which is trace elements in water, and then NIST 1549 non-fat milk powder, a food type matrix. So digestion methods. For the NIST 1643 water, we simply use the selenium pre-reduction technique without any digestion procedure, simply the boiling in the HCl. Again, for the non-fat milk powder, we used the FDA analysis manual, the EAM 4.4, to digest that sample. And again, this was done in the CEM Mars 6 system. So here we have excellent agreement. This is for the selenium, the trace elements in water, certified at 12 part per billion. We measured 11.7 for excellent recovery. And then also for the non-fat milk powder. So the sample preparation with the digests and the pre-reduction techniques, again, worked very well with the HGX 200 system. Okay. So in staying with the HGX 200 unit, we'll move then from the hydride generation reaction, and we'll look at a different type of reduction reaction, in this case, cold vapor. And this is going to be specific for mercury. In this reaction, we use a 2% stannous chloride solution and 7% HCl to reduce mercury plus 2, or ionic mercury, to elemental mercury. Elemental mercury, of course, in that form is volatile. One important note, this solution of stannous chloride and HCl was first sparged or cleaned for 20 minutes with argon to remove any traces of mercury from the reagents, either the stannous chloride or the HCl. This is in order to get the lowest blanks possible. So for here, our application, we're going to use the HGX 200 with cold vapor generation for improved ICP-MS detection of mercury in a muscle tissue sample. And again, this is also a marine type sample. So here's a general schematic for the cold vapor setup for mercury. In this case, since everything is acidified and our reagent is acidified, remember the sodium borohydride was kept in a basic form, we do not need to use that one mixing block for acid. We can then pump our sample and reagent, in this case, the stannous chloride, directly into the mixing block through the mixing coil and into the gas liquid separator of the HGX-200. Also, this reaction does not generate any byproduct gas such as hydrogen. So this reaction does tend to be quite stable, and backgrounds tend to be quite stable. I did want to show you one picture so you get a full idea of the scale of the HGX-200 versus a contemporary ICP or ICP-MS system. This is for the Mercury work, and here you see the HGX-200 placed on the bench next to a thermal ICAP RQ ICP-MS. So that gives you an idea of the relative size. In this case, of course, we would remove the standard nebulizer and spray chamber from the host ICP-MS and then connect the gas flows and the outlets directly to the HGX-200. You would, of course, use the peristaltic pump, or you could use a standalone peristaltic pump to pump sample solutions and reagents. And if you wished, you could certainly then automate this. You could bring over an auto sampler, not shown in the picture, to automate the samples after they've been prepared and move those through the HGX-200 and into the ICP-MS. So operating parameters. On this slide, I didn't include things such as the coolant gas and the auxiliary gas. Those actually stayed the same. I will point out again the nebulizer gas and the additional argon gas. We used about 0.9 liter per minute, same as the nebulizer gas, through the gas liquid separator where the frosted glass post is, and then the additional argon gas above the membrane filter at about 0.2 liter per minute. So that was really the only change versus the standard nebulizer conditions. So first we did a calibration, and so this calibration curve, of course, shifts lower with the use of ICP-MS. We used the mercury isotope at mass 201 for this curve, and we prepared a calibration curve 10, 50, 100, and 1,000 nanogram per liter, or part per trillion. Introduced those standards via the HGX-200 and had an excellent correlation coefficient of 495, so can certainly be used for analysis. Detection limit comparison, and again, this is on ICP-MS. At that particular mass, we can then push the detection limit below a part per trillion down to about 0.3 ppt. With ICP-MS, of course, how far down you can push often may depend upon the cleanliness of the reagents and the cleanliness of the lab. So as ICP-MS is so sensitive, you'll probably see perhaps a factor of maybe of up to 10 improvement in the detection limits, again, depending upon the cleanliness of the reagent, vessels, and the lab overall. So we then looked at this muscle tissue sample. There is the description of the tissue. It's an ERM muscle tissue sample, and it was first digested again according to the FDA elemental analysis manual, in this case 4.7. The mercury level at the instrument before dilution factor calculations was approximately 150 part per trillion, so that very easily fit on the calibration curve that we generated, and our measured and certified, the values agreed almost exactly. So the sample preparation and then the reaction with the stannous chloride HCl solution is verified. Now, one other important application I do want to mention about the use of this technique of cold vapor generation for mercury with the HEX200 is avoiding potential interference on a number of mercury isotopes. And this is for mercury isotope studies, particularly in geochemistry. I've listed there the 4 main ones of note. And if you are going to use a solution nebulizer, then tungsten, which is, of course, not uncommon in geological samples, can form an oxide combining with oxygen from injected water from a traditional nebulizer, and you can end up with those oxide interferences on those mercury isotopes. If a device like the HEX200 is used, the tungsten, of course, does not react. So it stays in the liquid and simply pumped out to waste. So that can be very beneficial if you are doing a study of mercury isotopes. And of course, it's certainly of interest. Mercury is a toxic element. It's a priority pollutant. So eliminating that tungsten oxide by using this type of reaction is certainly of note. Here are some selected literature references. There are more on the Teledyne CETAC website, but these are some noted ones. There's one for arsenic listed, and selenium, and for antimony. There are additional ones, including some of the other elements that we didn't talk about, such as germanium, but those are there. And at the end slide, I'll show you the link to the CETAC website, so you can refer to some of those additional literature references. Now, in the final part of the webinar, we'll move to our last part of sample preparation, and that's for using a solid phase chelation agent. In this case, it's composed of a polystyrene substrate that's been chemically derivatized with a chelating agent, in this case, iminodiacetate, and we're just going to abbreviate it as IDA. The SPR part stands for suspended particulate reagent, and we'll show you what that means in just a little bit via some pictures. This is supplied as a 10% suspension in slightly basic water, right around pH 8. It is typically used in a batch mode for sample preparation, meaning it's typically used offline, not online as with a column. The main application is going to be pre-concentration of trace metals in higher salt matrices, such as seawater and brines. So this is just a schematic of the chelating functionality. You have a polystyrene substrate. It's been chemically derivatized, and there's the iminodiacetate functionality, which does the chelation. As you move to a more basic pH and you remove the carboxylic acid hydrogens off, the exposed ionic oxygen, and also the double, the 2 unshared electron pairs not shown in the nitrogen, can then chelate or complex with certain trace metals, particularly divalent and trivalent metals. So this is what it actually looks like, and it simply looks like almost like a latex. This is a 10 milliliter suspension of 1 gram of this material suspended in 10 milliliters of slightly basic water. And it's then provided in a small bottle, in this case a 30 ml low density polyethylene bottle. Okay. The size of the solid phase reagent, the nominal diameter of what we call the beads is 10 microns. Okay. So just as a bit of background for the dissolved solids content of various water samples, seawater is approximately 35 grams of dissolved solids per liter, or about 3.5% total dissolved solids. Brackish water or estuarine water, like we looked at for the NRC SLU 2 reference, is about 10 grams dissolved solids per liter. That can have a wider range depending upon the estuary you're looking at, but in this case, about 1/3 of that of seawater. Freshwater, lakes, rivers, glaciers, less than a gram dissolved solids per liter. Tap water or drinking water is usually around 0.5 gram dissolved solids per liter. So it's the top two that we're often concerned about with this type of application. So just so you see one of these standards, this one is no longer available. I believe it's now SLU 4 or SLU 5, but this one was out of the St. Lawrence estuary in Canada, and these you could acquire in large bottles and then use as you needed for verifying your methods, as these were certified materials that would go through a variety of techniques to certify a range of elements that could be referenced. So just to show you what levels of dissolved solids you might find, and I always found this a useful slide. Deionized water on the far left, drinking water in the middle, and that was just from a municipal water source, and the estuarine water from the St. Lawrence Seaway. And you can see as you evaporate a set volume of those waters, you can see the very clean beaker, some residue from the drinking water, and certainly you have salt in the estuarine water. If you take that by a factor of 3, then you would see then the entire bottom of the beaker would be covered with salt if it was a seawater sample. So how do we then approach this offline sample preparation? So, and this is 2 slides, so I'll go through these steps carefully. So we'll take a 15 ml sample of a seawater reference material, and we'll add it up to the 15 ml mark of a pre-cleaned polypropylene vial. Now, again, this reagent we're going to use is a suspension, so we can actually pipette some of it. So we'll pipette a 0.1 ml aliquot directly, and then we'll add a small amount of yttrium. You could also use scandium as an internal standard. The pH then of this mixture containing the seawater sample and the suspension of the solid phase reagent is then adjusted from its preserved value from the supplier. It's preserved at 1.6 pH to approximately pH 8 using 2 aliquots of high purity ammonium hydroxide. So we'll first start with about 25 microliters, then 20 microliters, easily pipetted in, and then you well mix the sample. The SPR IDA reagent or beads are then allowed to settle for 1 hour, and then the vial is placed in a centrifuge and spun at 2000 RPM for 10 minutes. The supernatant liquid is then carefully poured off to waste. You want to minimize the loss of any of the bead material, the solid phase material, because that is going to bind the trace metals of interest. If you want, you can do at least 1 washing step. A solution of DI water adjusted to pH 8 with high purity ammonium hydroxide is added. You mix up again, and then you go through the same settling process, centrifuge it, and carefully pour off the supernatant liquid. The last part is where the user has a lot of control. You would then release the chelated trace metals using a high purity acid solution, in this case nitric acid, to extract any of the chelated metal ions. The extract solution can be diluted to whatever volume you would like, and then you can then analyze that solution directly on the ICP-MS. In this case, we used a cross-flow type nebulizer in case there were any fines, small pieces from the solid phase reagent. You might have to be a little bit more careful if you're using a glass concentric nebulizer. Certainly a cross-flow nebulizer or a V-groove nebulizer is certainly appropriate for this type of analysis. So some pictures just to show you what this looks like in practice. So this is simply a 15 ml tube filled up with the CAS4 nearshore seawater reference material. And again, this is from the NRC in Canada, so it's simply a clear liquid. That doesn't look that out of the ordinary. Then we'll pipette in this 0.1 mil or 100 microliters of this 10% suspension of the solid phase reagent, the suspended particulate reagent with the immunodiacetate functionality. And then against the black background, you can see, well, the solution looks a little bit cloudy, and that's as expected as the material is suspended throughout the seawater sample. Then as you allow it to settle, you can see the concentrated pellet of the beads or the solid phase reagent and bound metals move to the bottom. And of course, that will happen over time by gravity. But again, you can then accelerate this if you place this into the centrifuge. Okay. Now, sample quantitation was performed by the method of standard additions. So you, of course, have your unspiked seawater aliquot, and then you prepare spikes. And we did that at 0.25, 0.5, and 1 part per billion before addition of the SPR IDA beads. The sample preparation procedure was then used to produce the sample spikes, and we also did a reagent blank. So first we wanted to see, and we did this measurement by ICP optical emission. Well, how good a job does this do of reducing some of the high matrix components, specifically the sodium in the sample? And there you see the sodium is really reduced by about a factor of 500 from nearly 10,000 ppm down to about 20. There is reduction of magnesium and calcium, but not as much, because the immunodiacetate chelator does have some affinity for both magnesium and calcium. But of course, it'll have larger affinity for some of the elements of interest, such as copper, cadmium, and lead. So really the main matrix component we're worried about, sodium, and also the attendant chloride, which of course is not chelated at all, as it's anionic, is removed. I do want to point out, for seawaters, a lot of these are available from the NRC in Canada. CAS6 is the currently available form. There are other seawaters also available that you can access that are certified for verifying your sample preparation methods and techniques. So finally, we then did the analysis and found excellent agreement overall between what we found and the certified values. The one I would just point out is for uranium, that was a reference value we read back at 2.57, certainly in the general range of around 3 for the reference value given. You can see, though, some of the concentrations of the elements in this nearshore seawater are quite low, particularly cadmium and lead, which are of interest as pollutants. Lead is down at about 10 part per trillion. And again, that's challenging to see, particularly in a full seawater matrix. So sample preparation, like using this material, is certainly advantageous to both pre-concentrate a low-level element and to remove a lot of the salt matrix. So part numbers. In case you are interested in these items, there's one part number for the Hydride generator that's listed there, and a SP number, SP5646, for the SPR IDA solid phase reagent. That reagent, again, would be supplied as a 10 ml suspension in that 30 ml low-density polyethylene bottle. And again, you don't use a lot per sample. You're using typically about 100 microliters, so one bottle is good for about 100 samples. Interface kits. We supply interface kits for all of the current model ICP-OES and ICP-MS systems. The main ones here are listed. So if you did want to acquire an HGX 200, then you would also want to let us know what model ICP you intend to connect it to. One kit is provided at no charge with each HGX 200 order. So that would just be added as a line item so that you could then connect it to the system that you have in your lab. So finally, where to go for more information. There are email addresses for service and sales support. Certainly for technical support for questions about the HGX 200 or the SPR IDA chelating beads, you can contact myself at fred.smith@teledyne.com. And again, there is a lot of information, including additional literature references on the HGX 200 and the SPR IDA on the Teledyne CETAC website. So with that, I'll close the webinar for today. And again, if you have any questions, please send those in by email, and I'll respond to you as soon as possible. Thank you, everyone, for joining, and we'll probably be talking to you on additional webinars in the new year. Thank you.